First, let us learn about thermal conduction. Thermal conduction is a mechanism of heat transfer between two adjacent parts of a body, or between two bodies in thermal contact because of a temperature difference. For example, observe the person holding an iron rod at one end and placing the other end in fire. One end of the iron rod, which is in the flame, at a high temperature, and the other end at low temperature. Heat flows from the hot end to the cold end by thermal conduction. And as a result, after some time the person drops the rod. When heat is supplied at one end of the rod, the molecules in hotter regions gain kinetic energy and start vibrating faster. These vibrations are passed on to neighboring molecules through intermolecular bonds. In this way, the energy is eventually transferred to the whole body. Thermal conductivity of a substance, which is usually referred to as conductivity, depends on the state and nature of a substance. In solids, metals are very good conductors of heat. This is due to two reasons. One is that the molecules are very closely packed and thus help transfer vibrational energy quickly. The second reason is that metals contain a large number of free electrons, which also contribute to the quick transfer of heat energy. The free electrons close to the heat source receive heat and move faster through the metal. During this process, they collide with molecules and other electrons and pass a part of their energy on to them. In the case of gases, the molecules are far apart and hence the exchange of energy among them is very difficult. Therefore, gases are very bad conductors of heat. In the case of liquids, the intermolecular space is more than in solids and less than in gases. Therefore, the conductivity of liquids is greater than that of gases, but less than that of solids. Now consider a metallic rod of length L and a cross-sectional area A. Let the two ends of the rod be maintained at two different constant temperatures, T1 and T2. These temperatures are maintained by placing one end of the rod in a steam chamber and the other in a chamber with flowing water. Temperatures T1 and T2 are maintained in such a way that T1 is greater than T2. The end of the rod where the temperature is T1 is hotter than the other. Let us also assume that the rod is fully insulated and there is no loss of heat to the surroundings. Heat starts flowing from the hot end to the cold end. And after some time, there will be a steady flow of heat through the rod. The rate of heat flow is defined as heat current H. If delta Q is the heat flowing across any cross-section in time, delta T, then heat current H is equal to delta Q by delta T. Let this be equation 1. In a steady state, the temperature of the rod decreases uniformly from the hot to the cold end of the rod. The change in temperature per unit length is defined as the temperature gradient. Since the change in temperature for a length of L is T2 minus T1, the temperature gradient is expressed as T2 minus T1 by L. Let this be equation 2. It is experimentally found that in a steady state, heat current H is directly proportional to the temperature difference between the two ends and cross-sectional area of the rod. It is also found that H is inversely proportional to the length of the rod. That is, H is equal to delta Q by delta T, which is equal to Ka into T1 minus T2 by L. Let this be equation 3, where K is the proportionality constant and is called the thermal conductivity of the material. The SI unit of thermal conductivity is joule per second per meter per Kelvin or watt per meter per Kelvin. For a rod, the mathematical expression L by Ka is defined as its thermal resistance R, where L and A are the length and cross-sectional areas of the rod respectively, and K is the thermal conductivity of the material of the rod. Now, equation 3 can be written as heat current H is equal to T1 minus T2 by R. Let this be equation 4. Equation 4 is identical to Ohm's law of current electricity. This identity can be extended to some other cases as well. For example, if two rods of thermal resistances R1 and R2 are connected in series, then the equivalent thermal resistance R of the combination is expressed as R is equal to R1 plus R2. On the other hand, if they are connected parallelly, then the equivalent thermal resistance of the combination R can be found using the relation 1 by R is equal to 1 by R1 plus 1 by R2. Now consider two bars each of length L and a cross-sectional area A. The bars, made of different material of thermal conductivity K1 and K2 respectively, are soldered end to end, and the free ends are maintained at two different temperatures T1 and T2, with T1 greater than T2. In a steady state, heat current in the first rod is equal to heat current in the second rod. If the junction temperature is T0, then K1A into T1 minus T0 by L is equal to K2A into T0 minus T2 by L, or K1 into T1 minus T0 is equal to K2 into T0 minus T2. The junction temperature T0 is equal to K1 T1 plus K2 T2 by K1 plus K2. Since heat current through the combination is equal to heat current through the first rod, if the equivalent thermal conductivity of the combination of two conductors is K, then we can write Ka into T1 minus T2 by 2L is equal to K1A into T1 minus T0 by L. On simplifying, we get K into T1 minus T2 is equal to 2K1 into T1 minus T0. Substituting the value of T0, we get K into T1 minus T2 is equal to 2K1 into T1 minus K1 T1 plus K2 T2 by K1 plus K2. On further simplifying, we get K into T1 minus T2 is equal to 2K1 into K2 into T1 minus T2 by K1 plus K2. Therefore, K is equal to 2 K1 K2 by K1 plus K2. This is the expression for equivalent conductivity when two conductors are connected in a series. The table shows the thermal conductivities of some materials. Metals have very high thermal conductivities and hence conduct heat rapidly. Materials like wood, bakelite and wool are bad conductors. When loss of heat by conduction is to be restricted, the body must be surrounded by an insulating substance. For example, we use woolen clothes in winter to prevent loss of heat, as the air is entrapped in the pores of the wool fabric, which acts as an insulator. When heat is to be transmitted faster, good conductors are used in the process. For example, cooking utensils, water coolant systems in car radiators, and nuclear power plants all use good conductors.